Okay, so we're in section 6.6 today. And there's this handy little diagram at the top of 6.6, and I just want to make sure that you guys understand this diagram because we've got these 7 special quadrilaterals that we've studied. And so I just want you to understand they're all quadrilaterals, right? But then at the top level here, you basically got 3. We've got a kite, which we just studied last week. We've got a parallelogram. And then we've got a trapezoid. And so beneath the trapezoid, there was only one special trapezoid that we studied, the isosceles. Correct spelling that's optional. And then underneath parallelogram, we could split that up into 2. We could have a rhombus, or we could have a rectangle. And then the kind of most specific shape was the square. As far as the shape that fit in the most categories, the square is both a rhombus and a rectangle and a parallelogram and a quadrilateral, right? So the way to look at this chart is anything that's down here could also be classified as everything as you kind of follow the trail, everything that's above it as well, right? So if I asked you for the most specific or most exact name, then I'm expecting you to give me this name at the very bottom if it corresponds to one of those, right? Or if it's a rhombus, right? Parallelogram and quadrilateral would not be the correct answer. The most specific the most specific or most accurate, most detailed version of that to your shape would be rhombus here, or rectangle. But does everybody know what those are now? Like, are those firmly planted enough in your mind so that you could, if I said, for example, draw me one of those and label it so that I'm clear that that's what you're drawing, could you do that? Think you could do that? I'll talk through it real quick. What's a kite? What are the key characteristics of a kite? Like if you were to draw a shape, which was a quadrilateral, which means what? What's the basic definition of a quadrilateral, Ian?
A kite has 2 pairs of congruent sides, but the opposite sides aren't.
You're talking about a kite, right? Yeah, but then if I said a quadrilateral in general, so you're right. He's got the quad. So quadrilateral just means it has
4 sides.
4 sides, right? And then, like Ian explained, with a kite, I'm expecting you to do a drawing that. Tell me what you said again, Ian.
There's 2 pairs of congruent sides, but the opposites.
The opposites are not, right? So it would look like that there. So that would be a kite. What if I said draw a rhombus? Yes.
All the angles are equal.
All the angles are equal. So
wait, no, never mind. It's all the sides are equal.
All the sides are equal.
Sorry, I spoke with the...
That's okay. Which one would be all the angles are equal?
That would be a rectangle.
A rectangle, right? So in the case of a rectangle looks like this. All the angles are the same. For a rhombus, the length of the sides all have to be the same, right? And then the shape that fits into both of those, right, where the length of the sides and the angles are all the same, would be a square. Okay. Finally, trapezoid, which we drew at the beginning. Trapezoid has 2 opposite sides that are parallel, but the other 2 opposite sides are not. And then what makes it an isosceles trapezoid? Liana, I know you want to say it.
The 2 legs are equal.
The 2 legs are equal. That's right. So if you put a shoe here, a shoe there, these guys are equal, right? All right, excellent. Good job. Any questions about those shapes? Okay. So let's see if we can do some examples. And this is where I'm going to turn it over to you guys and give you an opportunity to work the example while I finish grading here. So what we're going to do is example 3. Okay? And example 3, we're trying to show that it's a rhombus. And so what are we trying to prove in order to prove that it's a rhombus? Somebody else. Since you gals are both on the board. Yes, Annalie.
That its sides are congruent.
Its sides are congruent, right? So all the sides have the same length. All right? Now, since this is on a coordinate plane, we can determine that by using what formula? Yes. What? What was it? I heard it. What did you say?
Distance formula?
The distance formula. That's right. So Grace said the distance formula, and she would be correct. So you're going to have to know the distance formula in order to do this. And if you do the distance between each of the points and they all turn out to be the same, you will have proven that this is a rhombus. All right? On your mark, say go. Wow, dude, this is great. So, did everybody get the right answer? Or did everybody get the same value for each of your distances? Yeah? All right, so I'm going to do one distance just to make sure we're all on the same page, just in case somebody was confused with it. But the process is the same, right? So the distance formula is what? If I have 2 points, let's say I have point x1, y1 here, and x2, y2 here, what is the distance between those 2 points? Someone else that's not on the board yet. Does anybody know? Sorry, ladies. Just trying to give someone else a chance. Joshua.
It'd be x2 minus x1 squared plus y2 minus y1 squared.
Squared plus y2 minus y1 squared. Is there anything else?
There's a radical sign.
There's a radical sign. It's a square root over everything, right? And we get this from basically the Pythagorean theorem is how we figure this out, right? So if you're comfortable with using the Pythagorean theorem and you could kind of draw the dotted lines here, right? You could figure that out on your own if you happen to forget the distance formula. All right, but that's correct. So this works for any 2 points that we want to pick. So we're just going to pick 2, 5. So we're going to find the distance between point 2, 5 and negative 2, 3. All right? Now when you're doing, it doesn't matter which point you make x1, y1, and which one you make x2, y2, as long as you make sure you don't take the x1, do x1, how do I want to say that? It doesn't matter, you can't do this. You can't make this point here x1, y2, right? And this point here x2, y1. So that's not allowed. That you can't do. So you have to be consistent. So the point is, whenever you're doing your distance formula here, whichever point you start with for the x value, you have to start with that point for the y value as well. Okay? So we're going to make this one here be our x1, y1, and we'll make this our x2, y2, right? So we're going to start with this point here. We're going to say negative 2 minus 2 squared plus, now we're going to start with the y here, and say 3 minus the y over here, 5, oops, all of that squared. Right? And so when we pay attention to our signs here, this is a negative 2 minus 2 is going to be negative 4 squared plus 3 minus 5 is going to give us a negative 2 squared. So, wait, did I start recording?
Yes.
I did.
Yeah.
Okay, all right. Just panic for a second. 16 plus 4, the negatives go away, right? So my final answer is the square root of 20. So in order to prove this was a rhombus, I had to do that for all 4 sides, right? I should get square root of 20 for all 4 sides, and that would have proven that. Right? You guys good? Okay, yes?
Isn't the square root of 20 2 square root 5?
2 square root of 5. So square root of 20 is the same as the square root of 4 times 5. Square root of 4 is 2, so yes, 2 square root of 5 would have also been a valid answer.
I just simplified it.
Yep. And normally that's what I would say do. I would say bring everything outside the radical that you can, but I think they left it square root of 20 in the book. I wouldn't have counted wrong if you hadn't brought it out, but either one of those would have been acceptable. Okay? Alright, let's move on to wow.
Once you get there.
I don't know. That might have been a student that time.
So kind of like biology. What's going on next?
All right, so we're gonna move on to that seems familiar. That song.
Sounds like a pirate movie.
Sounds like The Patriot. Maybe. You guys seen The
Just like
Patriot?
walk in there and be like, what are you walk in.
It's like I can't identify that song. Stop it.
Yeah, he's probably like,
Okay, I think there's someone at the door. All right, so what type of quadrilateral they ask is ABCD? This is example 4. So let's look at that one real quick. This is just, again, making sure that we understand all of our definitions. So they give us this one and they say this is 120 degrees, and this is 120 degrees, and this one is 60 degrees, and this one is 60 degrees. So this doesn't fit necessarily any of the descriptions that we've already given when I asked you guys how we identified these shapes, but it does fit something that we learned with one of our theorems concerning these shapes. And can anybody tell me what that theorem, at least tell me what that theorem says and what shape it's related to? 80.
If both of the base angles are congruent, then it is an isosceles trapezoid.
So this is an isosceles trapezoid. So if I gave you this figure here and I said, tell me, label the name of that figure, you would say this was an isosceles trapezoid, right? Because the base angles are the same for those guys. All right? Does that make sense to everybody? Does anybody happen to know off the top of their head what theorem that was? That was
theorem
6.14, right? So 6.14. So when you take your test, make sure you've got all these theorems on your note card, right? You know how to, you can identify all of those things that you know that. Like if I told you this was an isosceles trapezoid, you would know immediately that the angles had to be, the base angles had to be congruent. So if I gave you that on a test, right? And I said, and I've only given you angle C, and I said, I want you to tell me angle B. I only gave you angle A, and I want you to tell me angle B, angle C, and angle D. You could do that if I told you it was an isosceles trapezoid, right? Maybe I just drew it like that. Maybe I didn't even say isosceles trapezoid. I just drew that, and I put my little things there to show you that those are parallel. And I gave you one angle, and I said, give me all the other angles. And you would be like, no problem, because it's an isosceles trapezoid, so I know this angle has to be the same as that, right? And I know that these two angles have to be the same here, so whatever x is, that's got to be the same value for that. And so that tells me, I know that all the angles added together would be 2x plus 60 has got to equal 360, right? All the angles in a quadrilateral equal 360. And so that would be 2x plus 120 equals 360. That would be 2x equals 240. And so x has to equal 120, right? So I would know both of those angles were 120 degrees. Did you guys follow that? You can do that on your own? Okay. All right, so let's move on to the next section. Section 6.7, which is the last one we're going to look at in this chapter. Is this the last section in the chapter? I think it is. And we're going to talk about area. So have we calculated the area for any of these shapes so far? I don't think we've done that yet, right?
I don't think so.
Yeah. So we're gonna learn how to calculate the area for all of these special shapes. All right. Another good, something good for you to have on your note card. That's right. So postulate 22, I'm going to just abbreviate that post. 22 area of the square Alright? And so the area of a square is A equals S squared, where S is what?
Area.
No, A is area, S is,
Oh, I bet. I'm so
Side.
confused.
S is the side, right? S is just the length of the side, right? So you guys, that's one that you already know. I'm sure that one's no.
Some of us already know.
Okay, well,
Who
knows the
that? I don't know why I said area.
that's all right. That's all right. I was just trying to move on from it. You know, if you want to sit there on it, we can laugh, we can make fun of you. I can sit you in the desk of shame. Come on, no one sat in the desk of shame.
Desk of shame.
But what's the area of a what? Oh,
That's how I
it
felt
moves on to
30
what's the
seconds
area of
ago.
a rectangle? You guys probably remember that, right? If a rectangle is base and height,
Yeah.
what's the area? If we label the bottom part the base and we label the other side the height, what's the area?
Base times height.
Base times height. And so if base and height are equal to one another, like they are in a square, then it would make sense that the area of a square would be the side times the side, or S squared, right? I thought postulate 3 was going to be the area of a rectangle, so I got a little bit ahead of myself. But this one is the area congruence postulate. I'll write out postulate there. And that just says, let me write down this underneath it. If two polygons are congruent, so are their areas. Have the same area. Really, area is not something we would talk about as congruent. We would say the areas are equal. So if two polygons are congruent, then their areas are equal. Okay? That should make sense to us, right? If all the angles and all the length of the sides are the same for two polygons, then we would assume their areas would be the same. They're in essence identical figures. And then postulate 24 is the area addition postulate. And what this postulate says is that the area of a region is the sum of the areas of its non-overlapping parts. So to give you an example, one of the area formulas that I'm going to give you is the area of a kite. I'll let you guys finish writing that down. So why is it important that you write these down, that you know what they are? Because you might see that on a
Quiz/test.
but specifically, what'd you say?
Proofs.
You might see it on a proof, right? So you have to know what reason to give if that's on a proof. So all that means, one of the last formulas I'm going to give you in this section is what the area of a kite is, all right? But if I didn't give you the area of a kite, and basically when you draw the diagonals in the kite, it forms what?
Oh, plus.
It forms 4 right triangles, right? And so if you find the area of triangle 1 and the area of triangle 2 and 3 and 4, if you add all of those up, what do you have? You have the overall area for the kite, right? So that's all that area addition postulates say. Figure out the area of the various pieces and you add those together and you can get the area of the entire entire figure. So if we had like a figure that looked like, you know, like this, and then over here we had a little square off of that, and maybe a rectangle off of that, and we know the area of a rectangle, the area of a square, and the area of a triangle, we could figure out the entire area for the figure, right, by adding all three of those together. Okay, let's do postulate 25. No, not postulate 25, sorry. Theorem 6.20. I want to write that over here so we can keep all these high on the board. So theorem 6.20, this is area of a rectangle. And that's just, you guys have already told me that area is base times height. So if I draw my little triangle here and label this as the base and label this as the height, that's what the area of a rectangle. Did I say triangle? I meant rectangle. That shouldn't be news to anybody. You guys should have seen that somewhere before. What about a parallelogram? Now that one may not be one that you've used very often. Gabe, do you know what that is? Gabe's like, I use that all the time, dude.
It's base times height.
It's base times height, so that's kind of weird. But it sort of makes sense because if you think about it, a parallelogram is just sort of like a slanted rectangle, right? But the key is this. You have to recognize that with a parallelogram, it looks like this. This is the base, right? But the height is that distance there. Okay? And again, that makes sense to us if you think about just taking this rectangle here and like shifting, you know, the bottom from the top. Then our height would be that distance between the top and the bottom still. All right. Questions about those? I'm just going to do like an information dump on you and give you these formulas, and then we're going to go back and look at them. So stop me if you don't understand the pieces that I'm labeling or anything like that, right? So theorem 6.22 is the area of a triangle. Again, one that you guys should have seen before. And the area of a triangle is 1/2 base times height, right? When we label it like that, of course this forms a 90-degree angle here. I think everybody's seen that one, right? You guys used that one before. Theorem 6.23, area of trapezoid. And this one is the area equals 1/2 the height times the sum of the two bases. So area equals 1/2 h times b1 plus b2. And so if I were to label that, right, it looks like that. These are parallel. This distance here is h, and this length here is b1, and this length here is b2. Move this over here. Somebody see that? I'm not real happy with the way that I labeled this here. Just want to make sure you guys can see that. Can everybody in the back of the room see how I've labeled that? Yeah. I should bring like some little binoculars for you guys in the back. All right, just because I want to make sure everybody can see it, I want to write this up here. area of kite. And that is the area equals 1/2 distance 1 times distance 2. That actually doesn't stand for distance, it stands for diagonal. The length of diagonal 1 and the length of diagonal 2. So if my kite looks like this. We have two diagonals that are formed, and we know that these distances are the same. So this is we'll label this length here D2. And we'll label this distance here D1. So the length of the diagonals multiplied together, half of that will give you the area of the kite. And then we're missing one more figure that we need to find the area of our special quadrilaterals. Does anybody know what it is? Yes?
Rhombus.
We need to find the rhombus, right? So the area of a rhombus is theorem 6.25. Area of rhombus. And that is area equals 1/2. This one's also D1 and D2. And so, let's see. Draw it like this, just so it'll be a little easier to see. Kind of draw it like a diamond, where these are all equal to one another, and this distance here is D1, and this distance here is D2. So it's the length of the diagonals in the rhombus, okay? So I'll let you finish copying all that down, and then we'll see if you got any questions. I mean, the nice way about me giving it to you like this is you basically just got your note card, right? This is the stuff that you need to write on your note card to make sure that you understand. They're a lot wordier in the book, so I tried to just summarize it for you. And but I want to make sure that everybody understands the various parts that I've labeled. So does anybody have any questions about the drawings or the definition of the areas? Yes?
So if we were to use these in a proof, would we have to say theorem 6.20, or would we have?
You can just say area of kite
Okay.
or area of a rhombus, something like that. Would be fine. Okay? Who we got? Who is it? All right. Any questions? Anybody? Is anybody asleep? Everybody still awake? Oh, Cal's asleep. Okay. He's mastered the ability to sleep with his eyes open. That would be a cool thing to master, wouldn't it?
Like fish.
Huh?
I used to almost be able to.
Wow. How would you do that? Maybe if they made some special contacts that just kind of come down.
Yeah, I would do those.
Yeah. All right, so here's what we're going to do. I'm still not done grading. A couple of those took a little longer than what I thought. So I'm going to let you work on some more. And yeah, this is like this. Did you guys have Miss Hersey?
Mm-hmm.
So you guys had little whiteboards that you would lift up, right? So how did that work typically? Would she just give you a problem and then everybody puts their answer up? Is that how it works? Shows how
Yeah,
they work
yes,
it?
sir.
Some people would be faster than other people,
Right.
so she would have to
So
like.
some of you are like, I'm getting heavy, right? Yeah, so this is kind of what we're doing here. It's just like you're not holding it up for that reason. It's like everybody's going to be sort of finishing at a different time. So let me just let you work on this. Instead of doing the one that's in the book, how about I give you one? All right.
Mm-hmm.
So I want you to find the area of this figure. So I'm going to give you one similar to what's in the book. All right. But we're going to say that this is 10 and 13 and this right here. That way you can't just look and copy it down from the book, you know, you have to actually make sure you understand how to do it. So I want you to find the area of that figure. Just the area that's not dotted. But here's some additional information that they give you because there are two methods that you can use to figure this one out. All right, so everybody take a few minutes to try to work that one, and then we'll tackle it. So let me just go ahead and knock this one out because I mean, you might need a calculator. If we, oh, I think I see the problem, right? Yeah, I shouldn't have changed it because your numbers are gonna be different. All right, my bad. Sorry, guys. That's what I get for, again, modifying it on the fly. What kind of figure is this? Huh? It's a parallelogram, and so this is what we're doing, right? So, having done that, what you do need to be able to do with these figures is you have to be able to rotate them in your mind, right, to make sure that you understand. So let's just say that was 9, like I wrote it, and let's rotate this guy. If I leave it rotated like this, what would my numbers be? My base would be what? 10. My base would be this 10 right here, right? B equals 10. And what would my H be?
10.
My H would be, you said 13, but for parallelogram, you have to take the distance from here down to here. Right? So it would be the 10, the way that I've drawn it. And so it would have been 10 here. So doing it that way, I would have gotten 100 as my area. If I had rotated it in my mind, so that I had like one that looks like this, then this would have been the base of 13, and this distance here, based on what I put there, would have been 9. And some of you would have got a different answer if you looked at it that way, and that's why I didn't. I'm sorry, that was my bad. So base equals 13, and H equals 9. In this case, so 13 times 9, 9 and 12 is 108, right? And then another 9, 117. So 117 would have been your answer here. Does that make sense? I apologize if I confused you with that. All right, let's. We're basically out of time, but I want to do one more. All right, just real quick. Let's do the area of a rhombus, which is example 5. All right. How many of you have a class after this? All right, most of you? All right. So here's what I'm going to do. My next class is about to take a quiz. I've got like 2 more quizzes that I need to grade, so I'm going to grade these last quizzes. So if you want to come by and get yours after your class, feel free to stop by and pick up your quiz. I mean, I'll turn it into you next week, but if you want to go ahead and see it so that you kind of know how you're doing, then you can. For anybody that doesn't have a class after this, if you want to just wait outside the door when I do these last couple here and record the grades real quick, I'll get it to you. Okay? But let's do this. Let me do this real quick. All right? But let me just set this problem up, because I know some of you have to go. All right? So we've got this problem that looks like this, and they give us this, 20, 20, 15, 15, and they say find the area of this rhombus. Well, this one's actually pretty straightforward, right? So don't let it confuse you the way that they lay it out. The area of a rhombus, we were told, was just the distance, 1/2 times d1 and d2, right? So it would just be 1/2, area equals 1/2 of the length of one guy. 20 plus 20 is 40, times 15 plus 15 is 30. So altogether that would be 1,200, half of 1,200, which would be 600 units squared. All right. would be the value for that area. So there's all sorts of ways that these problems may be presented to you, but does that make sense to everybody? They're always going to give you enough information where you can do some sort of calculation and figure out the values that you need and then determine the area that way. Okay?